So this first video is about kinematics. That as far as the AP Physics C test goes, the goal here is to show where the calculus side of those kinematic equations comes from. I'm going to show you some of the deeper stuff, just so you kind of know where everything's going and then where it comes from. But you'll see that a lot of the problems are actually relatively straightforward. So when we're talking about position, velocity, and acceleration, we can interpret these in a calculus context as those rates of change, right? So on a derivative side of things, if we have a position, that's just that x of t right here, we can find its velocity by taking the derivative of that with respect to time, or the acceleration, take that second derivative of the position, which will get us that rate of change of the velocity. On an antiderivative side of it, if we start with acceleration, we can integrate the other way. So from acceleration, we can integrate the acceleration function to get the velocity, or integrate velocity to get to position. And so that's how all of those are related to each other. I know that you're given all those fancy formulas to calculate each one of these, but if you know one of them, you can easily find the others using that calculus piece. So just for fun, I really like going through where all of your formulas on your formula sheet come from. Don't look too far ahead. I'll go through this line by line. So let's start with acceleration. So acceleration at any given point in time, we talk about that negative g times j, where j is our component vector in the y direction. So that's moving straight up and down. So the negative g, what you're used to seeing, is the negative 9.8 meters per second per second. That's your acceleration due to gravity, and it's straight down in that j direction. So think back to the component vectors that you did in pre-calculus, or that you've been doing in physics. That's what our acceleration vector looks like. So if you're not as familiar with vectors using the ij components, again, if you think back to pre-calc, your vector 3, 7, this is just an example, would be 3i plus 7j, where I is that unit vector in the x direction, so you would literally plot 3 of those, like you can see in blue there. And then the 7j is the unit vector in the y direction, so you literally plot 7 of those going vertically. And then overall, the vector 3i plus 7j is the vector that starts at the beginning of the blue and ends at the end of the red. So when we're talking about the i's and j's here, that's directionality. So when we're talking about the negative g times our unit vector j, that unit vector j is vertical. So you're probably more used to that negative g being negative 9.8 meters per second directed into the ground in that y direction. So that's where the negative gj comes from. It's just telling us the directionality, turning that acceleration into a vector for us. So if we want the velocity at any given point in time, all we need to do is integrate our acceleration. So the integral of a of t with respect to t is just going to be our velocity v of t, which, if we integrate negative g times j, is negative gt times j, so just is a constant, so integrated by just multiplying by t. And then don't forget our plus c at the end whenever we do an indefinite integral. Now, what is that plus c? Well, that's going to come from our initial velocity. So if you find our v sub 0, just plug in 0 for t. That negative g times 0j is just 0. Then the plus c just becomes our initial velocity. Well, that's kind of nice. Now we have an equation for our velocity. V of t is the negative gt times j plus our initial velocity, v sub 0. On your formula sheet, This one is equivalent to the very first formula you have, the v sub x equals the v sub x naught plus a sub x t. That's talking about acceleration in the x direction, but it's essentially the same type of formula that you're dealing with there. So once we have our velocity equation, we can now go through and find our our position equation. And all we have to do is integrate velocity. So integrate velocity with respect to t, and that's going to give us our position vector. In calculus, we use r of t, but then your negative gt times j becomes negative 1/2 gt squared times j. The v naught becomes v naught times t, and then we have to add that constant d at the end. Well, now we can find the value for d by just looking at our initial position, r sub 0. So plug in 0 for all of those t's. These first two terms just become zeros for both, and we get our d is our initial position. So plugging that in, we get this nice formula for r of t equals negative 1/2 gt squared j, which is a vector j, plus t times v sub 0 plus r sub 0. At this point, this formula should start looking familiar to what you have on your formula sheet. Just to take it the rest of the way, just for fun, as a vector, your initial position is 0 in the x direction, that's the 0i, and then we'll use h sub 0 as your initial height in the y direction, and that's the h sub 0 times j. And then for your initial velocity, if we look at the x and y directions, your initial velocity is v naught cosine theta, and the y component, the j, is v naught sine theta. So those are the two components of your initial velocities. So let's plug those i's and j components into your r sub 0 and v sub 0 to get this equation right here. So you can see our v naught was taken up by this component vector, and your r sub 0 was taken up by your h sub 0 times j. Now, there is a lot going on in this equation right here, but with some simplification and some separation, we can see that there are some j components. These are your vertical components of our position vector, of the movement through space. And so at any given time, the j's tell us that height component, how high we are above the ground. And then the I component tells us how far we've gone in that x direction. Well, that should look really familiar to you. If we separate the y components and the x component into a vector x of t, y of t, we get x of t is v naught cosine of theta times t, and y of t is negative 1/2 gt squared plus v naught sine theta t plus h naught. And those are those primary kinematic equations that you use for projectile motion. So the equations for projectile motion come from integrating acceleration to velocity and velocity to position and doing just a lot of vector substitution in place of that to get these nice equations right here. So at any given time, with a particular initial height, an initial velocity, and initial angle of trajectory, we can find the position of any projectile over time, or at a specific time. Now on your formula sheet, it might neglect the sine theta, the cosine theta with that initial angle, and so it might just be the throwing something straight up in the air or dropping something straight down. In which case, the sine piece of that second equation might just be 1 if you're dropping at the 90-degree angle where sine is 1. So that might be closer to the formula that you have on your formula sheet. So ultimately, these are the equations that we come up with. Now, as far as calculus on the AP Physics exam goes with kinematics, these are formulas that you should be familiar with to use outside of the calculus piece. The calculus side of it focuses on the process I just showed you. The process of integrating or differentiating to get from acceleration to velocity to position, back to velocity to acceleration. So that's where our focus needs to be. So to demonstrate that, I want to show you some practice questions. And feel free to pause the video, take some time to try out the problem, and then start the video back up and you can see the full worked out solution here. So this is a typical question that you would have you can see on an AP test, where we're given a function for the position at any given point in time. And it's asking us to find the object's velocity. So if you're ever given a function on the AP Physics C test, you're probably going to have to take a derivative or an integral of that function. And so be thinking about that piece of it. So we have a position function, and we want to find the object's velocity at time t equals 1. So if we know the position equation and we want to find velocity, the velocity at t is equal to the derivative of x with respect to t. So the derivative of this would be 4 minus t. Now, my goal here isn't to teach you all of the calculus. At this point, you need to know this calculus. My goal is to show you how it relates to the physics. And this is it. We have a position function. We want to find a velocity function. Just take the derivative. And then we want the velocity at time t equals 1. So we can find the v of 1, which is 4 minus 1 to get 3, which is c. So as you can see, it's not a very difficult problem if you know the calculus and you know how to apply it to the physics piece. So let's try another one here. Same function or similar function, but this time I want you to find the average acceleration of this function. So we know the position, and we want to find the average acceleration. So there's a few ways to do it. I want you to try it on your own first, see what you can apply, but then we'll come back, start the video again, and I'll explain the process. So remember from calculus, when you're trying to find average value, we are taking the integral of whatever function we're dealing with. So in this case, if we want the average acceleration, we're going to want the integral of our acceleration. But then the average piece of it means that we have to divide that over our change, in this case, time. So find the total integral of acceleration, divide it by the length of time that it's happening over, and that will give you your average acceleration. So part of our goal here would be to try and find an acceleration function. So from our position function, 2 plus 4t minus t squared, notice it's a little different than the last problem, we can get a velocity function by taking the derivative, which is just 4 minus 2t. And then we could get the acceleration function by taking the derivative of that, which is just negative 2. Well, notice by getting to that acceleration function, we don't actually need our formula for average value because the acceleration is constant. The acceleration is just negative 2. It will always be negative 2. And so the average acceleration is negative 2. Now, if we got a function for a of t, then we would go integrate it from 0 to 2, find out what that integral value was, divide it by the length of that window 2, and we would get our average acceleration. But if we recognize that it's constant here, we don't need to do any of that extra work. So another similar kind of question. Now we have a velocity equation, 4 plus 3t squared. And we want to find its average velocity from t equals 0 to t equals 2. So we know the velocity. We want to find the average velocity. So feel free to pause the video, see if you can find an average velocity. So from a graphical representation, at t equals 0, we said that the velocity is going to be 4, and at t equals 2, the velocity is going to be up at 16, right? It takes a non-linear path to get there. So if we want the average velocity, we basically need to integrate all of this and then melt it down so that this will fill in that gap, right? So that's where if we integrate our velocity, so integrate the 4 plus 3t squared from 0 to 2, and then divide that by the length of that time interval, so divide that in half, that will then take that total area, melt it down into a rectangle, and we can just find that height. So you can see the work on the right side there of integrating the 4 plus 3t squared, plugging in the endpoints 2 and 0, subtracting those, and then multiplying by that 1/2. And remember that 1/2 out in front came from the width of our interval that goes from 0 to 2. So if that went from times 0 to 10, then we'd be multiplying by 1/10 and spreading that total velocity, out over that 10-second window. Right? In this case, it was 2. We end up with 8 meters per second for that average velocity. So then we get into some questions that are maybe a little more free responsey, where, in a free response question, it won't be all calculus stuff, but there might be 1 or 2 of the parts that require to use a derivative or an integral. And so I want you to be ready for those types of questions. So here we have a particle moving in 2 dimensions with a velocity function v of t is 4t cubed I minus cosine tj. Remember that I and j are just telling us the direction, that I is our x direction and j is our y direction. So from this, we can try and find an acceleration function in terms of time, and we can find a displacement. How far have we actually moved from t equals 0 to t equals 3? So pause the video here, see if you can solve these 2 parts to this question. So to get acceleration from velocity, we need to differentiate everything. And so taking the derivative of our velocity with respect to time, and we could just take the derivative of each of these components separately. And so the derivative of 4t cubed would give us 12t squared in that I direction. So that's the x direction. And then the derivative of negative cosine would be positive sine of t in that j direction, that y direction. And that's it. This is our acceleration as a function of time. You plug in the time, it will tell you what the acceleration is, both in the x component and the y component. Then if we want the displacement, this is like the change in position, we need to integrate that velocity. So if we want to integrate v of t, we can integrate each one of those separately. So we can integrate, and we're integrating from t equals 0 to 3. So we can integrate the 4t cubed, so that's t to the 4th power from 0 to 3 times our I vector. And then negative cosine, integrate that is positive, or negative sine of t. Integrate that from 0 to 3 for our j direction. So we get 3 to the 4th I plus minus 0 to the 4th I. And then we have the negative sine of 3j plus 0j, which is sine of 0, I guess. So sine of 0 is 0, 0 to the fourth is 0. So that gives us the 3 to the fourth I, which is 81I, and then the minus the sine of 3 times j. And that's our displacement. And this is our displacement with x and y separately. Our x's are being displaced by 81 units, and our y is being displaced by negative sine of 3 units. So here's another one for you to try out. Now we have an acceleration function. 4t plus 7 meters per second squared. And then we're moving just along the x-axis. So we're moving in a straight line. But at time 0, we have an initial position of 6. And at time 0, it's moving at 2 meters per second. So we have some initial conditions that we can use. So with this, as you integrate from acceleration to velocity to position, we need to use those initial conditions as your plus c that you're getting when we integrate. So using that idea, see if you can find how fast it will be traveling at time t equals 4, and then where will it be at time t equals 4. So we have a velocity question and a position question for you to try out. And then start it back up to check your answer. So you can see the work up here. We started with acceleration, and so we integrate to get velocity. And that's the 2t squared plus 7t plus c. Then to find that c, we can use the initial velocity of 2 meters per second. So plug 0 in for all the times. We want it to equal 2, and we just end up with c equals 2. Once we know that, now we can plug in 4 to that equation to get 62 meters per second as the speed of that object at time t equals 4. Then if we want the location of the object at 4 seconds, we need to integrate the velocity to get the position. We end up with another plus c at the end. You'll notice we have some crummy fractions in there. But if we plug in the t equals 0, we want it to equal our initial position of 6 meters. So 6 is equal to our c there. We get our position function r of t, and then plug in 4 to that. You'll notice that this does not work out very nicely. You can plug that in and figure out what it is. But what I will tell you is the questions that are on the AP Physics test are not testing you on your fancy mathematical computations and your extreme knowledge of calculus. They want to know that you know the physics. And so they're not there to trick you with a bunch of numbers. And so the numbers on the AP Physics test should work out quite nicely. If they don't, at least on the AP Calc test, I think you can leave an answer like that and have it still be counted correct. But the numbers themselves should work out nicely there. Now, the last type of problem that you will see on the AP Physics test as far as acceleration, velocity kind of stuff is concerned, deals with graphs. And being able to read a graph and know what the velocity and the acceleration vectors look like on a graph, and being able to find an integral or a derivative looking at the graph. And so there's a mix of problems in here that I'll just walk through for you so that you can see what this looks like. So first, we want to sketch the velocity and acceleration vectors at C and D. The velocity one should be relatively straightforward because the velocity, if this is a position graph that we're dealing with, the velocity is always tangent to that curve. All right, the velocity is a derivative of our position, and so it's a tangent line. In this case, a tangent vector. The acceleration is a little bit tricky because we need to very carefully read the problem. That it says that there's a constant x component of the velocity. So the particle's literally moving along this curve. That is the path the particle is taking. Its velocity left and right is the same. But up and down, its velocity is going to change. And so if we're trying to sketch the acceleration vectors, the x component of the velocity is always the same. It's constant. And so its derivative to get acceleration is 0. So a constant velocity in the x means 0 acceleration in the x direction, which means the only acceleration that occurs is in the y direction. As the curve changes direction, we're accelerating in that direction. Remember, acceleration is a vector. We could change the rate at which our velocity is changing. We can also change the direction of our movement. If you're going the same speed, but you turn and face a different direction, you change your acceleration, or acceleration has occurred because you changed the direction of that velocity. So we do have velocity in the y direction, and that always is going to point inside the curve like this, but the x component of those velocity vectors will always be 0. But this is where we get into the calculus piece of it. We want to calculate that y component of the velocity as a function of x. So if we want the velocity of the y component, then we need to take the derivative of our position function, the y equals x cubed minus 3x squared plus 1. Now, when we take the derivative of that, remember, we're tracking this movement over time. And so we want to find dy dt. But we're going to want everything in terms of x and v sub x. And so we don't want t's in our answer. So if we want to find dy dt as our velocity, what we really need to do is use our chain rule. So we find dy dx and then dx with respect to t. So we'll find the derivative of our path function with respect to x, and then multiply that by the derivative of x with respect to t, which, fortunately, we know from the problem is our initial x velocity, which is constant. So the derivative of y with respect to x, this is just your regular calculus problem, the 3x squared minus 6x. But then we multiply that by dx dt, which is just our velocity in the x direction. So it's the same idea of what we've been doing in this video. It's just in a different, slightly different format because we had to use that chain rule to deal with our variables. Hopefully you don't throw something like that at you on a question like this, but in a free response question, this kind of thing could be fair game. And then this sets us up for where v sub y is equal to 0. We can just take this velocity equation now, set it equal to 0, and figure out what x values that's going to occur at. And so we have the 3x squared minus 6x. We want that to equal 0. We could factor out a 3x and have an x minus 2. So it happens at x equals 0 and 2. Which should make some sense to you because on our graph, we get those slopes that are horizontal at x equals 0 and out at x equals 2. So the qualitative significance of this, so what does it mean that the component, y component of our velocity was 0? Our function is moving to the left constantly. But what this meant is that our particle was moving up, but has now stopped moving up and is now moving down. And at that instant, at 0 and 2, our particle is motionless in the y direction. It's still moving in the x direction, but in the y direction, it's changing from increasing to decreasing, and so it's stopped momentarily. We can do a similar kind of thing with this one. This is just dealing with it in terms of acceleration, calculating the y component of our acceleration. So you can pause the video if you want and take a minute, see if you can find that derivative. Same type of deal. If we want to find the derivative of our velocity with respect to x, that's the same thing as doing dv dt, which is our acceleration, times, or dx times dx dt. So dv dx, that is taking the derivative of what we saw on that last slide, which is the derivative of 3x squared minus 6x v sub x with respect to x times dx dt, which is v sub x. So go and find that derivative. We get 6x minus 6 times v sub x squared. And that v sub x again was that dx dt right here. So again, I have to deal with that chain rule as a part of this. But that a sub y equaling 0, so we can now set the 6x minus 6 equal to 0. Solve that, we get x equals 1. So what's the significance about this? What does this matter? Well, look at your graph. At x equals 1, so we had x equals 0, here's x equals 1, here's x equals 2. X equals 1 is where we change concavity. We go from being concave down to concave up. And so our acceleration has changed direction, essentially. Instead of curving downward now, x equals 1 is where it changes to start curving upward. If you think about the acceleration vectors that are going on, at A and B, our acceleration vectors are pointing downward. And they're pointing downward all along this curve. But once we hit x equals 1, now we're curving the other direction, and our acceleration vectors are pointing upward. So that's where our acceleration has now changed direction. And then the last one, suppose that the particle moves along the curve with constant speed. So now, instead of it being constant, just moving left and right and having the y speed up and slow down, what if it's moving along that path at a constant speed the entire time? All it wants us to do is sketch the acceleration and velocity vectors at points C and D again. Well, the velocity vectors are going to be the same. Right? Those are always going to be tangent to that curve. But when we're moving at a constant speed along a space curve like this, our acceleration vector is always going to be perpendicular to our velocity vector. So that won't be the case if you move constantly in the x direction. But if your x and y's are both variable and your constant is moving around that curve itself, it's always going to be perpendicular. The acceleration will always be perpendicular to that velocity vector. So the last problem that I have for this, I wanted to get some integration and differentiation on a graph problem, where we actually get to use the graph itself to do the integrals and derivatives. So here's the motion of a car on a straight track, modeling its velocity as a function of time. So I want you to see if you can answer some of these questions using what you know about both physics and calculus, and then start the video back up to see that explanation. So you can see the answers here. Number one, what happened to the car at t equals 1 second? Well, we went from a velocity that was increasing, so they were speeding up, to a velocity that started decreasing, going down. So presumably they put on the brakes. I don't know exactly what they would expect on an AP test, how presumptuous they would want you to be, but the car starts slowing down. So if you put on the brakes after accelerating, you'll start to slow down. That's what's happening at t equals 1. For B, we're comparing the average velocity between t equals 0 and 1 and between 1 and 5. And so remember, to find average velocity, this is where area comes into play. And it's calculus in the sense that we're finding the area under the curve, so the area of this triangle, and then dividing it by the width of the triangle. So 1/2 base times height is 20, or is 10, divided by 1, which is still just 10. So we could essentially take this upper triangle, put it down here, and make that little rectangle that it has a height of 10. For the next triangle, 1 to 5, that's a distance of 4 seconds, and the height is still 20, so 1/2 base times height, but then divide that by the base of 4, we still get 10 as our average value. So for this one, we're finding the area under the whole curve, but we're taking this upper triangle and putting it right here. And we can see that it's still going to have a height of 10 for that area. So we're not integrating stuff for this, but we're still dealing with that area under the curve. Part C, displacement. How far did it go? Well, that is the area under the entire function that we're dealing with. Now, when we're talking about area, that's the area under this triangle and the area under this triangle. So we could go and write equations for those functions, integrate them, or we can just find the area of a triangle. And then the area of this triangle on the right side is negative. Don't forget that that triangle has a height of -10. That was a point where the velocity is now negative. The car has stopped and is now going backward relative to where it started going. And so that's going to be negative displacement. And so find the area of each one of those triangles. We're integrating just geometrically. And we end up with 40 meters was the total distance of that car. Where we went forward 10, forward 40 more, and then backward 10 to get that total displacement. So finally, we have this same graph, but we want to plot the acceleration function and the position function. Now the acceleration function is relatively easy. The position function is a little bit more annoying. So for acceleration, as a function of time, we can look at the slope. Remember, acceleration is the derivative of velocity. If this is a velocity graph, then the acceleration is the slopes of this graph. So the slope of this first line, the first part right here, we're going up 20 and over 1. And so in that chunk of time, our acceleration graph is that interval right there in red. It's just a constant acceleration of 20 meters per second from 0 to 1. But then at 1, our acceleration has now changed. Our velocity has changed. And so the slope of this second part of the line from 1 out to 7, we go from the point 120 to the point -10, 7. Or sorry, 7, -10. So we went down 30 and over 6 from 1 to 7. So down 30 over 6, the slope of that is -5. And so we can just put an interval from -5. So I'll get rid of some of this other stuff here. So we are just looking at those two portions in red. That is the acceleration. It's the slope of the first part of the velocity graph and then the slope of the second part of the velocity graph. Now it's a little bit trickier plotting the position during the interval as a function of time. But I at least want to help you find the equations. Again, the stuff on the test should work out relatively nicely. You're going to see that these functions don't. But we can still find the positions. So in order to find the positions, we need the equations of these two segments here and here. So we start at the point 0, 0, we go to the point 1, 20, and then we end at the point 7, negative 10. So let's focus on this first equation right here. The slope of that line we said was 20, and it goes through the point 0, 0. So that's just the equation, let's see, f of t is equal to 20x, or 20t. So slope times t, the y-intercept is 0, but this is only for 0 is less than t, which is less than or equal to 1. Then at 1, it changes to this new line here. And find the equation of this line, we need the slope, which we said, if we use our slope formula, 20 minus a negative 10 over 1 minus 7. We get 30 over negative 6, which was negative 5. And then we can just pick one of those points. Y minus 20 equals our slope times x minus 1. If you like slope-intercept form, which would be good over here, y equals negative 5x plus 5 plus 25. So negative 5t plus 25, and that is from 1 is less than t, which is less than or equal to 7. So there's our piecewise function. And so if we want the position functions, we need to integrate these. So if we integrate f of t, we get our position function. I'm going to call it r of, go from v of t to r of t, becomes 10t squared from 0 to 1. And then negative 5t squared over 2 plus 25t from 1 to 7. So if you want to plot the position over time, you would be plotting those two parabolas right there. And just as a fun fact, you would get a graph. So we start out with the parabola 10t squared, so it would go something like this. But then it's going to switch to a negative 5/2 t squared. That's going to force our function to go upside down. And if you remember from that last slide, we stopped at a position of 40. And so this is our function speeding up, right? So that's the first line on our graph. And then we start to slow down, and then we actually start to go backward. So our position is starting to drop backward. So we got up to a maximum position right here at like 50, I think it was. But then we're going to keep on dropping until we got to our maximum position of 40. So this was the first 10, then we went up 40 more, and then we went backward 10 more. And that's what we saw in the last. So that's the idea with kinematics and calculus. Not all terribly difficult. Some of these are very straightforward. Others, like some of these free response ones with the graphs, can be a little more involved. And we just need to sift through what it's asking. But ultimately, if you can understand that position, velocity, and acceleration are all just integrals and derivatives of each other, and we just use initial conditions to find those constant c's that get added in our integrals or integrating between certain time values, they don't have to be incredibly tough.